Hello everyone, this is Tanya. I'm one of the TAs assigned to the Aircraft Stability and Control course taught by Professor A.K. Bosch. We will be going over the contents of the previous week and trying to solve the previous assignment and a few other questions. So what we studied in the past couple of weeks was dynamic stability of an aircraft. So the approximations, the linear approximations for CL and CM that we did initially involved only CL naught, CL alpha, and CL delta E. Now, two new terms have come into play due to Q and alpha dot. So these two terms, Q is the pitch rate and alpha dot is the rate of change of angle of attack. So both of these rates have the time component in them, which is why it only appears in the dynamic stability, only appears when we study dynamic stability. Okay. Similarly, for CM, we have these two new terms associated with Q and alpha dot. Now, as opposed to the previous cases, we are not just doing CLQ into Q because Q is not a dimensionless parameter. Alpha, CL naught, CL alpha, CL delta E, they were all dimensionless parameters. So delta E was radians, radian is a dimensionless parameter. Now Q and alpha dot are radians per second. Okay, Q and alpha dot are radians per second. So we add these other terms, QC by 2V. 2 is just a convention, but the other terms are added to non-dimensionalize this term. So when that is done, similarly CLQ and CMQ will also have to be modified. So CLQ is dou CL by dou QC by 2V. Similarly, CMQ is dou CM by dou QC by 2V. Okay, this 2 is just a convention. You can also avoid it. You can also omit it. It does not contribute towards the dimension. So you can omit it or you can follow it. But in this lecture, we will be following this convention. Now, what happens to an aircraft when we provide a pitch rate Q? When we provide a pitch rate Q, the angle of attack at the tail changes. Okay, so if this was your tail, when we provide a pitch up moment, so there is an increase in angle of attack. Okay, there is a delta alpha tail. This delta alpha tail is approximately equal to QLT by V. Q is the pitch rate, okay? This Q is the pitch rate. Now, when there is a change in angle of attack, there is also a change in the lift produced. Okay, so when we initially deflected the elevator down, and there was a change in the effective angle of attack, and there was a lift produced. Similarly, when the tail encounters an increase in angle of attack, there is an increase in lift. So there is a delta L. Okay, the delta L is given by this equation, and when there is a delta L, it produces a pitching moment about the CG. Okay, about CG, produces a pitching moment about CG, and this is a nose down moment, so there is a negative sign. The rest of the terms are just the force into the displacement. Okay, displacement LP, moment arm. This is similar to the delta L. Now from these two terms, we get the two derivatives CLQ and CMQ. CMQ, again, you must note that it has a negative sign because a positive change in lift produces a negative moment. That is a pitch down moment. Okay. Okay, the sign needs to be exclusively mentioned here because all the other terms here are positive. CL alpha tail is positive, VH is positive, efficiency factor is positive, momentum is positive, chord is positive. So it has to be mentioned, the sign has to be exclusively mentioned there. Now we equate the system, the aircraft system to a second degree of freedom equation, second order equation. So a typical system of this order is the spring mass damper. Spring mass damper is characterized by this equation. Okay, so just erase that. Okay. So spring mass damper is characterized by this equation. When we equate these two dynamic equations, we see that the term analogous to stiffness was K in a spring mass damper system. The term analogous to stiffness in an aircraft was CM alpha, the amount it withstands towards any perturbation. Okay, so the stiffness with which it withstands any perturbation, any disturbance. Okay, so that was CM alpha. It is a quantity of static stability, static longitudinal stability. It's a term that symbolizes that. And the term analogous to damping C is CMQ. Okay, so over time, does it come back to equilibrium? Does it diverge from equilibrium? Or does it oscillate to equilibrium? Does it come directly to equilibrium when subject to a perturbation? Okay, so if this was your equilibrium, when it's initially at the equilibrium and it's subject to a perturbation, does it diverge from the equilibrium, or does it converge back to equilibrium over time, or does it oscillate and converge back to equilibrium? Okay, that's okay. So how it approaches the equilibrium or goes away from the equilibrium is characterized by damping. For an aircraft system, that is a CMQ. Okay, so oscillation would be like this. Okay, and then it decays out eventually, or it goes away from equilibrium, or it comes directly without any oscillation towards the equilibrium. Okay, so this is characterized by CMQ. Now the state variables for spring mass damper were X and X dot. The analogous states here are alpha and alpha dot. Alpha dot is, okay, theta. Sorry, Q. Alpha and Q. So alpha and Q. So in the equation you can see, so it's Kx, so it will be Cm alpha into alpha. Here it's Cx dot, it will be Cmq into Q. Okay, so these are the two states in our case, Q and alpha, and in their case it was X dot and X. Okay. Now we look into what are the forces that are acting on an aircraft and what are the frames used for this dynamic stability analysis. The forces acting on the aircraft are of three kinds: aerodynamic, gravitational, and propulsive. Aerodynamic, we know their lift and drag. They depend on relative velocity, V. Okay, so their lift and drag. They depend on the relative velocity. So if the aircraft is stationary, the velocity with which the wind is hitting the aircraft, or the velocity with which the aircraft is moving in air. So relative velocity determines the aerodynamic forces, that is L and D. Gravitational force G acts perpendicular down. Propulsive force is thrust. Okay. So now, as we discussed in the previous two lectures, it is easy for us to measure the propulsive force and the aerodynamic forces in the body frame, right? So it's easy for us to measure those in the body frame. But when we do dynamic analysis, our equations of motion, Newton's equation of motion, this one, and the moment equation, they are both defined in inertial frame. So this is differentiated in inertial frame. This is inertial frame. ZK, just ZK, where I, capital I, J, K are in the inertial frame. So this is inertial frame. Then you define the same vector in the body frame. I, J plus AZK, where small IJK are body frame unit vectors. Now you differentiate the same vector first in the inertial frame and then in the body frame. So when you differentiate that, you get this relation. How do you get this relation? So when you differentiate this, you have, so if you do it in inertial frame, how do you get it? You do dAx by dt into I cap plus ax into d I cap by dt, and so on and so forth for ay and az. Now these terms di by dt, dj by dt, dk by dt will be zero, will be identically zero, because we assume our inertial frame, our assumed inertial frame, that's the earth-centered inertial frame, earth-centered, earth-fixed inertial frame. We assume it to be inertial. So what it means is it is fixed. Have you been able to see, have you been able to hear, was there a break?
Yes, ma'am, there was a break, but now it's fine.
Okay, so I'll just continue. Okay. So when we differentiate in the inertial frame, we get these two terms and so on and so forth for ay and az. But these terms, that is di by dt, dj by dt, dk by dt, will all be identically zero. because our inertial frame, that is the one we have assumed to be inertial, that is the earth-centered, earth-fixed frame, we assume it to be fixed in time. So di by dt, dj by dt, all of them will be 0. So we'll only have these three terms. Now, similarly, if you differentiate it in the body frame, there you will have all 6 terms. You will have dAx by dt small I cap plus ax di cap by dt, so on and so forth for the other 3 directions. So you will have total of 6 terms, where this di by dt, dj by dt, they are all represented by omega cross I, omega cross j, and omega cross k. Okay, so where this omega is the angular velocity with which this body frame is rotating. It is given by this equation. So small ijk are body frame. All of these terms are represented in the body frame. Okay, small ijk are body frame. So p, q, r are the components of omega in the body frame. So after we solve this and substitute these two, we get this relation, where the derivative of a vector in the inertial frame is equal to the derivative of the vector in the body frame plus angular velocity into the vector. Okay, we use this relation in our 2 equations of motion, that is the force equation of motion, moment equation of motion. So this dvc by dt is differentiated in the inertial frame. We measure these terms in the body frame, so we have to equate these two. Using this equation, we get this, right? So this vector here, vector that we've considered in place of a, we will take vc. Okay, so dvc by dt in the body frame and this omega cross vc. Similarly, for the moment equation, we have dh by dt in the inertial frame. The vector here that is in place of a, we will use h. So dh by dt in the body frame plus, this term is not there, omega cross h. Okay, now these are the various terms and their components in the body frame, various terms that we use in the dynamic analysis and their components in the body frame. So we have force, we have vc, so uvw in the body frame. Omega we have discussed. Moment vector, you have L, M, N. So L is the rolling moment, M is the pitching moment, and N is the yawing moment. Similarly, you have H. H from here, you have Hx, Hy, Hz, which was derived in, I think, a couple of weeks ago. Okay. So now when we substitute all of these equations, all of these terms, we get the final 6 degrees of freedom equation as this. You have Fx, Fy, Fz, and you have L, M, N. Okay. So now you can, what we have studied previously for the static analysis, we have taken steady state condition. When we take steady state condition, what happens? These terms vanish. Okay, so there is no change with respect to time. Similarly, the product terms vanish when we assume equilibrium, right? So there is no relative angular velocity. So if you do such simplifications, you get your initial equations. So Fax equal to 0 comes at some point, which gives you lift equal to weight and thrust equal to drag. Okay. Now, this was the dynamic stability, the 6 degree of freedom equations. Now, how do you measure orientation of your aircraft? You cannot measure that with respect to body frame because you need to see how your body frame is oriented with respect to inertial axis. So we use one of the notations called Euler angles. Euler angles are psi, theta, and phi. Now, psi is not to be confused with yaw. It is the rotation about ZE. ZE is the inertial axis in this case. Now, after performing this rotation about ZE, rotation of angle psi about ZE, we get a new system of axis. It is X1, Y1, Z1. Now, when we rotate about this new Y1, we get this theta of Euler angle. Again, not to be confused with pitch. Okay. And after this rotation, when we do the final rotation about x-axis, phi about x-axis, you get your final axis system. Okay. Final axis system is nothing but your body frame. Okay. Now, these Euler angles appear in these two terms in our 6 degree of freedom equation, where in the gravitational forces are these terms. Okay. And PQR. So PQR, the omega terms. In these two terms, in these two quantities, our Euler angles appear. They do not appear in the aerodynamic and the thrust forces because they are measured in the body frame. Okay, so this has to be, the gravity is oriented in the inertial frame. Okay, so it will be oriented, it has to be rotated into the body frame when we write the equation in the body frame, because this Fx, Fy, Fz, like we mentioned in the previous slide, they are in the body frame. So when we represent the entire equation in the body frame, this fgx, fgy, fgz are also in the body frame. But mg is acting perpendicularly down in the inertial axis. Okay, so that is why you have these Euler angle, the orientation angles coming into play here. Now in the previous class, I had asked why this term, this psi, doesn't appear in any of these terms. Why? Because if you imagine your aircraft to be oriented as such, okay? So it is like this, and your weight is acting perpendicularly down. This is theta. So initially, you resolve this mg along, so you resolve it along parallel to the fuselage reference line and perpendicular to it. Okay, so along the thrust direction, let me just erase that. Parallel and perpendicular to the oncoming velocity. Okay, so that what you do this mg sine theta. Okay, mg sine theta will be along x-axis. When you do mg sine theta, it comes along x-axis. Then when you do mg cos theta, and then after rotating it about theta is about which axis? Y-axis. After rotating it about y-axis, then you rotate it about x-axis, the roll. What happens then is your mg vector is aligned with your z-axis. So then no matter how much you rotate about the z-axis, the psi, your mg vector will be along the z-axis. So even if you roll it, yaw it, it will still be along that axis, okay? Which is why psi does not appear in any of these equations. Okay, so moving on, we see that we take from the 6 degree of freedom equation, we take only the longitudinal equations. So longitudinal motion is characterized by motion along x-axis, y-axis, and rotation. That is pitching up, pitch down, rotation about y-axis. So you have u dot, v dot, and q dot. Now we apply the small perturbation theory. So we assume the aircraft is flying at equilibrium, steady state in our case, and then you perturb it. You apply small perturbations in velocity, in omega, in the Euler angles, in the force, and in moment. Okay, so you apply small perturbations in these vectors. Small perturbations are characterized by these small letters u, v, w, p, q, r. These terms with subscript 1, so u1, v1, w1, or psi1, phi1, theta1, they are all the values at steady state. So what is the velocity in x direction at steady state? u1. The perturbed quantity is the small u. Now, after performing various simplifications and taking a stability axis is taken along the velocity direction. Why? When we take the stability axis along the velocity direction, velocity is represented only in that direction. It does not have components in the other two axes. So it simplifies our equation greatly. So the stability axis is chosen only for the simplification purpose. Okay. So after performing all of these simplifications, we get these three equations, three perturbed equations of motion. It gives you small u dot, small w dot, and m. Okay. So yeah. Now we take linear approximations of each of these terms, each of these forces and the moment. Force in the longitudinal, for the longitudinal forces. Okay, longitudinal motion. Longitudinal forces Fx, Fz, and moment m. Okay. Now we take linear approximations as such, and again we do this u by u1 to non-dimensionalize. Okay, we do this u by u1 to non-dimensionalize. Now we take the first case, the first equation, and we find out each of those derivatives. Dou fxa by dou u by dou 1, dou fxa by dou alpha, dou fxa by dou delta e. Okay, so it's computed as such, where CD1 is the drag coefficient at steady state. CDU, what is CDU? Dou CD by dou u, that's u by u1. Okay, so now we know how the drag varies, how CD varies with Mach number. So it's constant up to 0.6 Mach, then it increases and then it decreases. It increases till Mach 1, this is 0.6 or 0.7. And then beyond Mach 1, that is for supersonic range, it decreases. Okay, so when you simplify this, you get m1 dou CD by dou M. Okay, this is CDU. So this is what you get. Similarly, CD alpha, CL1, CD delta E. Okay, so after you substitute these three terms in the first equation, you get your final equation of motion in the x direction as this. Now we represented by XUU, X alpha A, X delta E, and this G theta cos theta 1 comes from the original equation. Okay, it comes from here. Divide throughout by M and you get this G theta cos theta 1. Remember again, this theta is the perturbed quantity. Theta 1 is the quantity at steady state. Now here XU is nothing but this term. X alpha is nothing but this term. X delta is this term. Okay, so we represent all three directional forces and moments in this manner. Now we take the second equation. Second equation is in the z direction. Here we, okay, so previous case, let me just discuss that. Here in the first equation, we are not taking the variation with respect to alpha dot and q. Why? Because they are negligible quantities in x direction. There will be no, it will be negligible variation in forces in the x direction due to pitch and a change of angle of attack. Okay, so we are neglecting those terms in the first equation, but those two terms play an important part in the last two equations. Okay, so similarly we conduct the analysis for the second equation where we can't compute the 5 different terms, 5 different derivatives. Now this negative is coming in these two new terms. Why? Because your force is in the upward direction, lift is in the lift direction, but lift is in the opposite direction as to your z axis. Okay, so there is a negative sign because of that. Now we discussed in the previous class, why are we bringing in alpha dot into the picture? Because when we want the aircraft to fly at a particular angle of attack, it takes time to achieve that angle of attack. It doesn't directly reach that angle of attack. So over time, your angle of attack varies and reaches the desired value. So if there is a variation with time. Similarly, the downwash effect. Downwash effect was what? So you have your wing at this place and tail at this place. So your wing cross section. Okay. So, and this is your tail. Now, due to the finite wing, you have vortices. The velocity of the air flowing from bottom surface of the wing and the air flowing above the surface of the wing, they mix at the wing tips and there are vortices formed. These vortices, when they flow back, there is a downwash. So there's an effective reduce of angle of attack that is seen at the tail. Okay. Now this downwash takes time to build, takes time to reduce this angle of attack at the tail. So it has to travel from here and go till here. So it happens over time. Okay. So the downwash also varies with time. These are the two reasons why we have to consider alpha dot. Okay. So in now these new terms, we have terms involving CLQ and CL alpha dot. They're given to us by these expressions. You can see that CL alpha dot has this d epsilon by d alpha. So that is the term that is varying with time. So that comes into play in your CL alpha dot. Substituting all of these terms gives you the final equation in the z direction. Okay, so w dot. That's not omega, that's w. Now the third and the final equation of motion for longitudinal motion is the moment equation, pitching moment equation. So again, you have 5 derivatives that are given here. This is fairly simple as opposed to the previous case. It's straightforward. All of these terms we know. Now, like the previous case, the new terms are CMQ and CM alpha dot. CM alpha dot, again, you can see that there is a downwash term. Downwash term is the one that depends on time. So that is available in the CM alpha dot equation. CM delta E, we have studied multiple times previously. So these 3 terms are the new ones that are appearing in this equation. Substituting these derivatives gives us the final equation of motion in the pitching moment equation. Okay, so third one, Q dot. Okay, so these give you the final equations of motion. I've just put them together. So the first equation, we had seen how we represented those large coefficients as XU, X alpha, X delta E. This is done similarly for the other 2 cases. So you have ZU, Z alpha, ZQ, Z alpha dot, Z delta E. And these are the terms coming from the main equation. So this also comes from the main equation. And for pitching moment, you have MU, M alpha. It's supposed to be M alpha subscript into alpha, MQ, M alpha dot, and M delta E. Okay. Now you represent all of these. You apply a Laplace transform on all of those and assume Q to be, not assume Q to be, Q is theta dot. So if you take the Laplace transform, you get S theta of S. Okay. Q of S is S theta of S. Now you apply Laplace transform on all of these equations to get this and represent it in the matrix form. So this S theta of S is, it comes here, okay? That is why you have an S square term here. Instead of writing Q of S, we write S theta of S. So this is the final matrix, which is of the form AX equal to B. Okay, where this is A, this is X, this is B. Okay, this is simplified matrix form where XU, ZU, MU, X alpha, Z alpha dot, M alpha dot, ZQ, MQ, they're all coefficients that represent those large coefficients in these three previous equations that we derived. Okay. Now, when we take the determinant of this matrix, when we take the determinant of this matrix of A, you take determinant of A and set it equal to 0, you get the characteristic equation of that matrix. The characteristic equation is of this term, is of this form. Okay, so you have 4, S power 4. Okay, it's a polynomial of order 4. Now, how do you find the roots of this equation? You can find it numerically. Okay, that is the only way. There is no other simplification. Now, for stability, for dynamic stability, we apply the Routh criteria. Routh criteria says what? One of the criteria is A, B, C, D, E. All of these coefficients have to be greater than 0. That is one criteria. The next criteria is this one. B, BC minus AD minus B square E should be greater than 0. Okay. So after we took one of the conditions, that is E greater than 0, we analyzed this separately to get this. What is this? Cm alpha by Cl alpha should be less than Cmu by Clu plus 2Cl1. Okay. Now, so for a subsonic case, what we see is the Cmu. So Cmu is again similar to the CDU that we had seen. Cm, and this is Mach number. So it's constant up to 0.6, increases from 0.6 to 1 Mach, and then decreases for the supersonic case. Okay, so for subsonic case, largely for the subsonic case, the Cmu is 0. This Cmu for subsonic is 0. So for subsonic case, Cmu is 0. What does that mean? Your Cm alpha by Cl alpha is less than 0, which is, we know this, right? So this is the static stability condition that we had studied. dCm by dCl should be less than 0. Now for a supersonic case, for supersonic, we have Cmu less than, it's negative, right? So it's negative. So you have Cm alpha by Cl alpha less than some quantity A star. So if you take this quantity as A star, it should be less than some quantity A star. It is less than 0. It is less than 0, but it should also be less than A star. What does this tell us? What does it tell us is, suppose for a subsonic case, if this is your neutral point, your CG can be anywhere behind it. So, I mean, ahead of it, okay? CG can be here, CG can be here, anywhere ahead of it. It will maintain this condition of Cm alpha, Cm alpha by Cl alpha less than 0. For a supersonic case, it should not only be ahead of neutral point, but this distance should be less than A star. Okay, it should not just be less than 0, it should be less than A star. That is the difference between subsonic and supersonic. Okay. Now the roots of this equation, that is AS4, BS3, they come in two pairs of complex conjugates. What are complex conjugates? So you get of the term A plus or minus IB, C plus or minus ID. Okay, so you have 4 roots and they are obtained such that they are two pairs of complex conjugates. Okay, so when you have a complex conjugate root, it signifies oscillatory motion. Okay, so it can either decay, so it can either decay, or it can expand. Okay. So now if your root, if A and C is negative, the real part is less than 0, it decays. Okay. If A and C are greater than 0, it expands. It does not decay, it does not come towards the equilibrium, it goes away from it. So when we analyze for dynamic stability for our aircraft, we see that the roots have negative real part. So both A and C are less than 0. Okay. Now, how do we characterize these two equations? One with a greater A. So if A is greater than C, okay, what does it mean? So your final solution will be e power at, where A is less than 0, and e power ct, where C is less than 0. So when A is greater than 80, it decays fast. Okay, so the exponential curve goes very fast to the equilibrium. Now when C is small, it takes time to go to the equilibrium. So it takes long time. So this is characterized by long period mode, and this is given by short period mode. Okay, so when subject to a perturbation, these two roots bring it to the equilibrium fast because A is large. These two roots bring it to the equilibrium after some time. So it slowly oscillates and comes towards the equilibrium. Okay, this is the difference between short period and long period. Long period is also referred to as phugoid. Now we'll just briefly go over the second order system. Second order system is T. So mx double dot plus cx dot plus kx is equal to f of t, again spring mass damper system. Now how do you find the characteristic equation of this? We take x equal to e power lambda t. Okay. When you substitute it here, you get this as the characteristic equation. When you solve for this, you get two roots that are given by this. Now, the relation between this c by 2m and km give you whether it behaves oscillatory or not. So if c by 2m is less than km, this will be negative. So root of negative will give you complex conjugates. Complex conjugates means oscillatory. If c by 2m is equal to k, you get repeated roots. Okay. And if c by 2m is greater than k, what do you get? You get either positive or negative real roots. You don't get complex roots. Okay, that determines whether it oscillates or does not oscillate. Now, when you compare it to a typical second order system, which has eta, damping ratio eta, and omega in natural frequency, these natural frequency is given by root of k by m, and damping ratio is given by c by 2 root km. When you substitute these into the main equation, you get your typical second order system. We know this equation, right? We know this equation. So just a review of a typical second order system. Okay. So now we'll go over the questions of the previous assignment. Okay. So let me try. Yeah. So given is y double dash minus 5y dash plus 6y equal to 0, and you've given two initial conditions. What will be the value of y of t? So they've asked you to solve this. Okay, let me just do it. Okay, so they've asked you to solve this equation. How will we solve it? So I told you initially that we can take y of t to be e power a t. Okay. So when you substitute it, you get the characteristic equation. What do you get the characteristic equation as? You get a square minus 5a plus 6 equal to 0, right? You can take a or lambda or anything, it doesn't matter. So this is your characteristic equation. Next step is to find the roots of this equation. What are the roots of this equation? So you get a plus 3, a minus 3, a minus 2 equal to 0. So the roots are 2 and 3. Okay. So your final equation will be of the form y is equal to c1. c1 is some constant e power a1t plus c2 e power a2t. Okay. Just a second. Yeah. So when you substitute the initial conditions, that's y of 0 and y dash of 0, you will get the values of c1 and c2. Okay, so y of 0, you just substitute directly, you get c1 and c2. c1 you get as minus 2. Sorry, you get as 4, and C2 you get as minus 2. So when you substitute this equation, finally what you get is C1 is 4 e power, that's minus 8, you get 4 e power minus 2t minus 2 e power 3t. Okay, so that is this one. Okay. Okay. Now next question is, for the system shown below, find the value of a damping ratio. Okay. So now equate this denominator to the typical second order system that we know, that is s square plus 2 eta omega n s plus omega n square. So what do you get? Omega n square is 20 and omega n is root 20. Then 2 eta omega n is 8. So eta is 8 by 2 omega n, that is 8 by 2 root 20. How much is that? 8 by 0.894. So that is this value. Next question is, for the system shown below, what is the time response for step input? Okay, so in the previous class, I told you a trick to get the answer when the graphs are given. What we do is we find out eta. Okay, eta is the damping ratio. Again, you equate this to a typical second order system. So you take s square plus 2 eta omega n plus omega n square. So you get omega n as 3 and eta as 1.5. So eta is greater than 1. Eta greater than 1 is what? What is the condition called? What is the condition called when your damping ratio is greater than 1? Can someone tell me? What is the condition called when your damping ratio is greater than 1? Overdamped, yes. So overdamped. How do you characterize an overdamped equation? It's either this, so there is no oscillatory behavior. That's what you need to remember. Either this one, or this one. Now, what is the difference between overdamped and critically damped? Okay, so overdamped is eta greater than 1. Critically damped is eta equal to 1. Okay, eta greater than 1 reaches the equilibrium like this. So it reaches the equilibrium without any oscillation, but after some time. Now critically damped case reaches the equilibrium soon, very fast. Okay, so at this point it reaches the equilibrium. Your overdamped equation, it reaches the equilibrium after some time. So it goes something like this. This is critically damped, this is overdamped. Okay, so for eta greater than 1, this is the equation. Now we'll see how to solve this. How do we solve it? We take the inverse Laplace transform of this CS. Okay, so I'll just take a fresh page and solve it. So we take C of S as, what was it? So the transfer function C of S by R of S was, what was it? 9 by S square. S square plus 9S plus 9. And your RS, that is the input, is 1 by S. Okay, so R of S is 1 by S. Now we take this term and we split it. We'll see how we can split it. Okay, the denominator. So S square plus 9S plus 9, we write it as S square plus 2 into eta into omega n into S plus omega n square. Right? Second. Yeah. So now what we do is, I'll just put in the numerical values also. S square plus 2 into 1.5 into omega n was 3 S plus, So we add one term here and subtract one term here. So what do we add here? 1.5 into 3 square. Okay. Now we do this omega n square, 3 square. And this term we subtract 1.5 into 3 square. Okay. So this remains same. Now we do a simplification. So what we get is s plus 1.5 into 3 the whole square minus 3 square. I take out 3 square common from this. Okay. 3 square 1.5 square minus 1. Okay. Okay. So now we do C of s. So you multiply that R of s over there. Okay. So you get 3 square by 1 by s comes here. You get denominator as s plus 1.5 into 3 whole square minus 3 square 1.5 square minus 1. I just substituted this value in the denominator. I expanded the denominator here, that I substituted into this. And this R of s is 1 by s, so that I have multiplied here. Okay. So now what we do is this denominator a square plus b square, so a plus b into a minus b. So we do 1 by s 3 square by s plus 1.5 into 3 a plus b 3 root of 1.5 square minus 1 into a minus b s plus 1.5 into 3 minus 3 root of 1.5 square minus 1. Okay, this is, I've just taken this term as a square minus b square. So a square minus b square is a plus b into a minus b. That is what I've done here. Now we take partial fractions. So how do we take partial fractions? You get a by s plus b by, I'm just going to simplify these terms. Okay, I'm just going to substitute the numerical values and get the final term. So you get b by s plus, just do that. So it's square root of 1.5 square root of 1.5 square minus 1 minus 1 into 3 plus 10.5 into 3. So you get s plus 7.854 plus c by, you subtract that value. So you get 1.5 into 3 minus that quantity, you get 1.146, s plus 1.146. And when you do these partial fractions, you get values a equal to 1, b equal to 0.1708, and c equal to minus 1.1708. Okay, you get these values. So now you take the inverse Laplace transform. You get inverse Laplace transform of both sides. So inverse Laplace transform this side and this side. You get small c of t equal to inverse Laplace transform of 1 by s is 1. The inverse Laplace transform of the other term, that is b was 0.1708 by s plus 7.854 is plus 0.1708 e raised to minus 7.854 t. And this will be minus 1.1708 e raised to minus 1.146 t. Okay, so this will be your final answer into u of t, into whatever the signal r of t. Okay, so your final answer would be this one. This is the correct answer. You get the same value here. Okay. Now we go to the next question. Next question is a similar transfer function, but the difference is in this middle term. So here what you get eta as, can someone tell me here eta will be what? What will be the value of eta here? What is the damping ratio in this case? Compare the denominator to a typical second order system. So it's s square plus 2 eta n 1. Yes. So damping ratio 1 is what? What is the condition called? Damping ratio 1 is characterized by, what is it given by? Critically damped. Okay. So which will be the right answer here? Just look at the graphs and tell me which one will be the right answer. Critically damped also reaches your equilibrium without any oscillations, but faster than overdamped. So which will be the right answer? Which will be the right answer? We see overdamped was this one, right? Sorry, overdamped was the first one. Fourth one, correct. So your answer will be this. Now we'll see how to get your value C of t, okay? So similar to the previous case, we'll just take a question. So we'll start with C of S. C of S was what? 9 by C of S by R of S is 9 by S square plus 6S plus 9. Again, R of S, it says unit step, so R of S is 1 by S. Okay, so again we take the denominator, we take partial fractions. So C of S is what? Is 1 by S into 9 by. So this you can factorize this, okay? So you can factorize it into S plus 3 into S plus 3, right? Correct? So you can factorize it. So when your damping ratio is 1, you have repeated roots. So in this case, the repeated roots are -3 and -3 that I had discussed earlier. So when your damping ratio is 1, critically damped, you have repeated roots, repeated negative roots. Okay. Okay. So now we take partial fractions. That is A by S plus B by S plus 3 plus C by S plus 3 square. Again, when you solve it, you get A equal to 1, B equal to -1, and C equal to -3. Now, when you apply inverse Laplace transform, you get C of t. So apply inverse Laplace transform on both sides. So you get C of t as 1 by S inverse Laplace transform is 1. Then you get, so it's -1 by S plus 3. You get -1 into e raised to, what was the root? Roots are -3, -3. Okay, so you get e raised to -3t. Since there are repeated roots, you have minus t e raised to -3t, and the coefficient in this case is 3. Okay, so that is your final answer. You can see that that is what is given here, right? 1 minus 3t to the power of -3t minus e to the power of -3t. So this is critically damped. This is the right answer. Okay. Okay, this will be +3. No, sorry, it will be -3. Okay. Now we go to the next question. Here, what is eta? Here, what is eta? Eta equal to 0. So it is undamped. Undamped means the oscillation continues. There is no damping. The amplitude of oscillation doesn't change. So it has to be this answer. It has to be this one. Okay, so eta is 0. So it's undamped. Now it's how to get to that. Again, we do the same. C of S by R of S. C of S by R of S equal to 9 by S square plus 9. Now you do C of S equal to 3 square by S into S square plus 3 square. Again, you do the same partial fractions, take inverse Laplace transform, you get, so again 1 by S, you get 1. So when you do this, what you get finally is 1 by S minus s by s square plus 3 square. So that is cos 3t. Okay, so it's a continuous non-decaying oscillation. This is the right answer. 1 minus cos 3t. Now we see the three approximations that we do for the main characteristic equation, that is ax. So this was your main equation, ax equal to b. So first approximation is short period mode approximation. Here we assume that when the aircraft is flying, it's subject to a small perturbation. It varies and comes back to equilibrium soon. Okay, so it has a large root. The negative real part is large. So it comes very fast to your equilibrium. So in short period mode, you assume the perturbed u to be small, okay, over the entire duration. So when you assume it to be small, assume it to be constant, there is no change, you can neglect this first row and the first column. So your final equation would be this. It would be a 2 cross 2 matrix. It will be this and z delta. Okay, it will not have the first row, first column. Okay. Further assumptions that we make are z alpha dot, zq, and theta 1 are all 0. Okay. When you substitute these assumptions, the characteristic equation for short period mode is given by this. Then you equate it to a typical second order s square plus 2 eta omega n s plus omega n square, typical second order equation, and you get omega n for short period mode as this, and omega damping ratio for short period mode as this. Similarly, we do for phugoid mode or the long period mode. Here we assume that when your aircraft is subject to a perturbation, it slowly oscillates and comes back to equilibrium. But during the oscillation, we assume the alpha to be constant, which is not really true, but it's a fairly good approximation. So in this case, we neglect these crossed out columns and rows, and you get again a 2 cross 2 matrix where you have this, 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 this. You don't have alpha dot, you don't have this one. Okay, you get the other terms. Okay, so the same assumptions are made here. ZQ theta 1 are 0. When you make these assumptions and solve it, you get this as your final characteristic equation. Again, equating it to the typical second order system, you get the natural frequency and damping for phugoid mode as these two. Okay. Next thing is called pure pitching, which we can achieve in a wind tunnel, but not in real. So here again, okay, alpha is assumed to be one, that needs to be removed. Pure pitching, what happens here is that, so your flight path angle is between oncoming velocity and horizontal, and this is alpha. So this is alpha and this is gamma, this is velocity, this is fuselage reference line. Okay, this entire thing is theta. So we take theta equal to gamma plus alpha, and in pure pitching, there is no flight path angle. So your velocity is oriented along the horizontal. It comes in the same direction. There is no change in velocity in the wind tunnel. So we take gamma to be 0. So theta equal to alpha. Okay, using this approximation, we have the pitching moment equation here. And in terms of, so these are non-dimensional terms, Cm alpha dot, Cmq, and Cm delta E are non-dimensional terms. Now M alpha dot, Mq, M delta E are all dimensional derivatives, dimensional terms. Okay, they have dimensions. They are not non-dimensional because they have this half rho v square sc by Iyy. Okay, so half rho v square sc by Iyy into Cm alpha is M alpha. Okay, so this should have M alpha dot. Now we take the pitch rate to be same as theta dot, and we know theta is alpha. We just saw theta is alpha. So pitch rate is nothing but theta dot is nothing but alpha dot. Now if you do q dot, it is alpha double dot. When we apply Laplace transform on this, you get q of s as s alpha of s. Now using all of these terms and these approximations, we get the characteristic equation as such. The pitching the natural frequency and damping ratio are given as such. Now this is just a comparison of the characteristic equations, damping ratios, and natural frequencies of the three cases. This is short period, this is phugoid mode, and this is pure pitching. Okay, So you can see that the short period mode has one additional term compared to your pure pitching. Why does that come? Because in pure pitching, there is no up and down motion. There is no motion along x-axis and z-axis. There is no plunging. There is only change of angle. Okay. So this additional term comes due to the translational motion, due to the non-rotational component of that motion. Okay. So that is the difference between short period and pure pitching. Similarly, in this damping ratio also, you have that additional term. This one that comes by virtue of this plunging motion. Okay. We'll just go over a few questions of this assignment. We will not solve it. So they've given you the four roots, the four roots of that a square plus b s cube plus cs square plus ds plus e. So they've given you the four roots of that equation. So you have two pairs of complex conjugates like we mentioned before. So it is, what are the roots? It's 0.002 plus or minus 0.1 j. You have minus 4 plus or minus 2j. Okay. So these are your two pairs of complex conjugate roots. First question is, roots for short period mode are. Okay. So we had discussed previously, short period mode reaches fast towards the equilibrium. So it has a large coefficient, which is why it reaches fast towards the equilibrium. For a long period mode or the phugoid mode, it takes a longer time, meaning the coefficients are small. I will not tell you the answers now, but it's fairly simple. Now, how do you find out the natural frequency and damping ratio for a phugoid mode? Okay, so you have the two roots. So how do you find the characteristic equation given the roots? So you have S plus or minus, I'm not very sure. Just a minute. Yeah, so it's S square minus sum of products, sum of roots into S plus product of roots equal to 0. So this will give you S square plus 2 eta omega n S plus omega n square equal to 0. Compare the terms and you will be able to find out natural frequency and damping ratio. Okay. Next question is, consider the following equation for a system. Find the range of K values necessary for dynamic stability of the system. Just a minute. So consider the following equation for a system. Find the range of K values necessary for dynamic stability of the system. How do you do this? You take the Routh criteria. We had taken two Routh conditions. One was A, B, C, D, E should be greater than 0, and the other condition. So if you take those two conditions, you will get two conditions for the value of K. So they will fall within a range. You will be able to solve this. So with this, we finish this week's tutorial. Does anybody have any questions? Does anybody have?
Yes, ma'am. I have a question.
Yeah.
Ma'am, regarding the final exam of this course.
Yes.
Ma'am, the paper pattern, how would be it?
It would be multiple choice questions only.
Ma'am, the same way we have in the assignments?
Sorry?
The same way we have in the assignments,
Yes,
like some.
yes. Same way. I think we will also have some numerical value type questions.
Yeah. Those two are the only types?
Yes. Those two are the only two types.
Okay, ma'am. Thank you, ma'am.
Anybody else has any other question? Okay. If not, we'll end. I'll just give you the link of the YouTube sessions. I'm not sure if it's being uploaded. So I will just paste it in the chat box here. Just a minute. So this is where all of the lectures are uploaded. This will also be uploaded in some time. So if there are no other questions, then we'll end it here. Thank you. We'll meet again next week.